Okay, so good morning, everyone. So we'll begin our lecture today. And so, if you remember last class, we did dynamics, last lecture. We worked out dynamics, and we saw that it just came from Hamilton's principle, or principle of least action. And we did a couple of examples. We worked out the Lagrangian flash action for a particle, a bead rather. Okay, so my original intent was to solve it in today's lecture, but complete solution will be in problem set 5, the next problem set. Okay, it's a beautiful, this is a beautiful example, and so today we begin a very important. So today, what we're going to do is we're going to study central force motion. Okay, so rather I should say motion under a central force, under the action of a central force. This is what we want to do today. And so we will just write out the, so first is what is a central force? Okay, so we'll begin with a particle. So under the action of a conservative force. Okay, so this force is minus gradient of some potential. Okay, so the Lagrangian for this system okay, so this is a general case. Okay, now we'll specialize. Okay, so we say that a force is central, a conservative force, is central if V is a function of only R. Okay, that means, so let's say, right? So R is okay, so it's independent, depends only on the distance from the origin. Okay, so here in this example, origin is a special point. Okay, so here the origin is a special point. And so if it's the origin and P is some point of observation, arbitrary point. So you join O and P. Okay, so the force is parallel or anti-parallel to OP. Okay, so if it's anti-parallel, that means it goes from P to O, it's attractive, and it's repulsive the other way from the origin. So origin is a preferred point, and F it's not even, no need to write partial derivative because it's only a function of one variable, so it is just dV by dr times ER cap. Okay, so this is what is ER cap, so I will specify this. I'll say this is a unit vector along increasing R. Okay, so in this setup, you pick a point P and the unit vector, in this case, would be in this direction. You choose some other point P prime, and then you just draw again, just draw that line. Okay, here it will be along this direction. So ER, okay, so we'll work in spherical polar coordinates. So this is a unit vector. So we will see reasons. It is yeah, go ahead. Somebody's asking a question. Okay, so let us try to understand what these spherical polar coordinates are. R, of course, we already defined. I'm sure all of you know this, but it doesn't hurt to write this thing. And R belongs to 0, and infinity, of course, is not infinity. Okay, then what is the other? Theta and phi. So cos theta is Z by R, and tan phi is Y by X. Okay, you can do the inversions, but theta belongs to the interval 0 to pi, and phi belongs to, it's a circle variable, so S1, or we can write it as 0 to 2 pi. Okay, so this is a circle variable, this is a segment kind of variable, as I explained earlier. This thing. So we'll define along. I'm sure all of you have seen these things in okay, so we'll just call them as ER cap, and unlike Cartesian unit vectors, these change from point to point, and they depend on theta and phi here. E theta depends only on theta, is independent of phi, and E phi cap is only a function of phi. Okay, these are things you can prove. Okay, so what we will do is I draw some picture now. This is the origin. So P is some random point. I think I made it too big, so let's reduce the size. Yeah, this is good. Okay, so we already seen, so this is the point P, and so increasing along this, and theta is this angle. This is, oh God, sorry. Okay, so this is theta, so increasing theta will go like this. So move the P out of there. So this is E theta cap. And phi is a rotation in the xz plane, so it will be E phi cap will be going, is directed downwards in the into the plane. Okay, so that would be shown. It's at this point. It depends on the point. So it is, you should see the tail of the arrow if you remember that convention. Okay, so these are the thing, and they form a right-handed triad. Okay, so that is ER cap cross E theta cap. What should this be equal to?
E phi.
E phi cap.
Okay, and so how will, one more thing, what is the rating? Yeah, go ahead.
E theta should be a function of phi also. Because if you go to a different axial angle, then the direction of E theta vector changes.
I'll let you think about it, okay? So let's put a question mark here and you can come back and tell me that I'm wrong. E theta is a function of phi, that's what you're saying. Yeah, that's correct. That's correct. Thank you. Okay, so and what is R? The vector R, it's along ER cap, and what is its magnitude? Okay, so now we want to ask, but you can see that this R vector depends on everything because the phi dependence and theta dependence is buried in here. Okay, so we want to ask what is a small displacement? What is a change in R if we take R to R plus delta R, theta to theta plus delta phi, and phi, sorry, delta theta and phi, to change it by that, right? So we want to ask what is the displacement generated by these guys, and the answer is okay. So let me actually do it in this fashion. Okay, so they are changing the points, and if you work this out, you get, by definition, these things. So you will get these things. Okay, so whatever I return is based on my definition that these things are unit vectors along increasing r, theta, and phi. So you're changing them so that it has to be along those directions. So these parts work out. But there are prefactors called scale factors, and I'll write them for you now. It's 1 here, it's r here, and here it is r sine theta. Okay, so these are called scale factors. And again, so what is a velocity? Okay, so velocity is dr by dt. So you just have to define. So you can just divide this above thing. So we get r dot er cap plus r theta dot e theta cap plus r sine theta phi dot e phi cap. So this is the velocity in spherical polar coordinates. Okay, so volume element is just multiplying you can do it from dx plus dx dy, but the volume element in this thing is just the product of the scale factors, r square sine theta, dr, d theta, d phi, or r square, dr, d cos theta, d phi. Okay, so we can work out what momentum is, linear momentum that is, that's just m times v, and we get this thing. So I have an exercise. Obtain the formula for acceleration. In spherical polar coordinates. Okay, so what I have in mind is A is dv by dt. This should be something times er cap plus something else times e theta cap plus something else times e phi cap. So you have to determine these guys. That's what I mean. Okay, so maybe this is an exercise. Maybe I'll put it in the problem set, or you do it yourself. Okay, so we need to compute, say, L, the angular momentum, which is defined to be R cross P. So we have expressions for R and P. So if you just go ahead and write it, we get, so we have worked out what P is here, and we know what R is. Okay, so you can see I was just setting up notation. And so now if you just go ahead, and so this will be just R er cap cross P, which is a slightly more messier expression, but we have everything that we need. We know that er, e theta, they form a right-handed triad. So for instance, e theta cross e phi will be er cap, and so on and so forth. So there are all these expressions that we know. So when you do the cross product, if you do that, you will get m r square minus sine theta phi dot e theta cap plus theta dot e phi er cap. E phi cap, sorry. Okay, the reason there cannot be a er cap top, er cap cross er cap is 0. Okay, so this is a very trivial thing, but we'll also compute one more thing. Let's say we want to compute Lz. Now that is a little bit more involved. It's just Ez, unit vector along the z direction, dot with L. Now you need to know what Ez cross E theta is, okay, and what Ez cross E phi is, but that's again very easy if you go to this picture that we have. Okay, so you can see this is Ez, and E theta. So you can see that Ez cross E theta is minus sine theta. Okay, you can just do this thing, but you can also see that Ez cap dot E phi cap is 0 because it's going out of the plane. Okay, so there'll be only one term which can contribute, so that will just become, so you get a sine theta coming from this and the minus sine theta, everything works out and you get m r square sine square theta phi dot. Okay, so this is an important formula. Okay, so now we want to write, so what is the Lagrangian? What is the Lagrangian? Again, there's something we worked out, some things in spherical polar coordinates. Okay, so L is half mv square, and we have worked out what those terms are. So if you can, we have worked out v, so we just have to dot it with itself, and you get. Okay, not L, this is T, kinetic energy. So I did mention it, but I keep using it. It's convention to use T for kinetic energy. Okay, and V is just V of R. Okay, so L is. Okay, so now we want to ask what are the canonically conjugate. Okay, to the generalized coordinates, to the generalized coordinates r theta phi. How do we do that?
LR by del R dot phi dot.
Yeah, so dr by dr dot, and that is just mr dot. Okay, and we also computed Lz or Lz. We got mr square sine square theta phi dot, and lo and behold, we get this. So P phi is also Lz. Okay, so you can see that these two have dimensions of angular momentum. Okay, so P theta, P phi have dimensions, physical dimensions, that is. Okay, but PR is mr dot, so it has dimensions of it has just dimensions of linear momentum. Okay, so I'll just pause here. Any questions, comments? Okay, so everything is crystal clear. I have to pat myself on my back for teaching, doing such a wonderful job. So let's make some observations. Okay, so let's come back here and look at the Lagrangian. Okay, so first point to observe here, which I'll write in yellow, is phi does not appear. So what do we say if a coordinate doesn't appear in the Lagrangian?
Corresponding momentum.
Yeah, and we say phi is cyclic. A cyclic coordinate. Okay, so the first observation is plus P phi This implies P phi is a constant of motion, so that's equal to mr square sine square theta phi dot, which is equal to Lz is a constant of motion. Okay. Now we already made this observation that P phi is this thing. So let us now look at so now we need to look at equations of motion. So Euler-Lagrange not equations, because I'll write only one equation for, say, theta now. What does that say? It says that do I want to do that first, or do I want to? No, I want to do something simpler. Okay, so I want to say that that means L, the vector L itself, here we have shown Lz is a constant of motion, L is a constant of motion. Okay, so what is L but? L is R cross P. Okay, so dl by dt will have two terms, which is dr by dt cross P using Leibniz rule, and R cross dP by dt. Correct? But what can we say about the first term here? It's dr by dt is V, so this is equal to 1 by m times P. So what is P cross P?
0.
Okay, so this is 0. Okay, and dP by dt by Newton's law is the force, right? So equal to R cross the force. Okay, but force, so the point is force is some f of r or minus gradient of shouldn't use new things, minus dV by dr for a central force times er cap. But and r is r er cap. Okay, so what can we say about f cross r? That's also 0. And it is 0 because it's a central force. Okay, so the conclusion, the total angular momentum, the angular momentum is a constant of motion whenever the force is a central. Is this point clear?
Yes, sir.
Okay. So now implications. So I'll make a claim now and prove it. Okay. So motion.
Sir, here we
Is
consider dr dt is equal to 0 because radius is fixed. That's why.
no, it's just V. So what is dr by dt is V. V cross P is 1 by m times P cross P.
Okay.
It's actually very simple. Huh? Okay. So motion is restricted to a plane. And the question is which plane? Okay, so question to you is, how do we prove this? Or at least tell me which plane.
So it will just be
Perpendicular
R
to
cross
L.
P plane.
Okay, so yeah, so first, if we know this, we are already in business. So we know that L is a constant of motion. Okay, so it doesn't change. So what will happen is that you draw this plane, and there's a normal vector to the plane. So this is the normal vector. This is some normal vector, and this will be along L. Okay, so in general, the equation of a plane in 3 dimensions is of the form some linear equation, A dot R equal to some constant. Okay, and you can prove exercise, show that the normal to the plane is parallel to A or anti-parallel. Okay, let's not worry about that sign, we can fix that. Okay, so now what can we say about the equation for the plane that we had? So what should be the equation for this plane?
L dot R is equal to constant.
Constant. Okay, so for our example, okay, so now we need to still fix the constant. What is a constant? Okay, so we need to fix the constant.
0.
Yeah. Okay, somebody said 0, which is correct. How do we see that?
L is R cross P.
Exactly. Okay, so the constant, so since L is R cross P, this just becomes 0. Okay, so it's trivial statement that L is perpendicular to both R and P. Okay, and so a little bit long-winded. You could have done it in 5. I'm sure smarter. You guys are smarter than me, so you will do it like in 10 seconds or something. But for me, this is what we get. Okay, so this is it. So this is the crux of central force motion. But we can do simplifications. Okay, so what we do is WNLOG. This is just defined to be with no loss of generality. Okay, we can choose our z-axis. To be parallel to R. To L, sorry. Okay. So once we do that thing, then the motion is restricted to the XY plane. Okay. And in spherical polar coordinates, what is the XY plane equation? It's theta equal to some constant. What constant?
Pi over 2.
That's it. Okay, so now you can see that the equations of motion in this special choice, we only have two variables to play with. Okay, which is r of t and phi of t. Okay, so we need to solve for these things, but we have a constant of motion. So first thing is we know that L now is just some number times Ez cap in our coordinate system. Okay, but we know that this is and what is L, which is nothing but P phi, which is because P phi was Lz we had shown, so that is m r square sine square theta phi dot. But what is sine pi by 2? It's 1. So this is equal to m r square phi dot. Okay, so phi dot becomes okay. So this is the first part of our thing. So so we solved for phi dot. Phi dot we can get if we know r of t. We have to do one integration. We still have to do one integration. But we can also use energy. So second constant of motion okay, there is no explicit time dependence, so Te, which is equal to T plus V, is conserved, is a constant of motion. Okay, so you have to go back and write all those things and then put theta equal to this and put theta dot equal to 0. Get rid of all those things, you get something very simple.
Since here we fix the theta so that our p theta will vanish, right? So
Yes.
only one.
Yeah, exactly. Okay, so we get half mr dot square plus L square by 2 mr square plus 0. Okay, so what determines E?
Kinetic energy plus potential.
Yeah, I know, but this is just fixed by initial conditions. Right? That's all I wanted from you. Nothing deep, I mean. Okay. So now we can actually use this and we can write r dot as plus or minus square root of 2e minus what do we have to do? Divided by n. No, I missed a 2 somewhere. This is okay now? Please check this, I make mistakes.
Yes, sir.
Okay, now it's okay, no? So now we can solve this. Of course, there is a sign which we have to fix, but that's okay. Depends on where you are in the orbit or whatever. So this can be written as dt equal to dr divided by square root plus or minus. So whatever is that complicated thing, but that's a function only of r. There's no time sitting out here. So we can do this, and you can formally integrate it. Formally means you may not be able to do the integration, but formally one can integrate this. By saying that t equal to integral 0 to t dt, and then whatever, this, you have to put some limits of over here. Correct limits have to be done. Okay, so now that we have r of, so this will give t as a function of r, but you can invert it. Which you invert. Again, this is only in words, you can't always do it. Invert to obtain r of t. Once we get r of t, we can go ahead and phi can be given by phi dot was what? L square by 2m r of t. And this implies that phi is some formalism again, some integral L by m 2m r t. Okay, so this is okay. So this is what we get, and so I'll pause here and for some questions. Okay. So there's just some more things. If you look at this again, let me point out this thing. If you look at this thing, it looks like a part, if you think of R as a system of 1 degree of freedom, but what you get is an effective potential of this variety. And this has, when there is L is non-zero, you can see that this is also like, so you get effective, this we write as V effective of R. And this is called a centrifugal barrier. Why is it called as this thing? Centrifugal barrier. You can see first thing is that when R equal to 0, it blows up. So it's becoming very, very large. Further, if you work out what the force is, you'll find that it's a repulsive force. It's repulsive and goes to infinity as this is. And so other behavior might be determined by what is there by V of R, but you cannot just go into so the when L is non-zero, the particle cannot go through the origin because there's an infinite barrier. It looks complicated, but if you think about it, what is L? It's R cross P, and it's a constant of motion. And if it goes through the origin at that instant in time, we can evaluate L. That means R is 0, so 0 cross anything is 0. So that, lo and behold, L should be 0. So only when L, the angular momentum, is 0, can it pass to the origin. Otherwise, there is some minimum distance it can go. Okay, this is something which you know. Okay, so that's a beautiful issue. Okay, so what does it mean to have a closed orbit? Is that let's say you will be at some r, theta, and phi, and you wait for some time period, it returns to the same r, theta, and phi. Okay, for instance, it could come back to the same radius, but it may not come back to the same values of theta and phi. That's not a closed orbit. So if you look at it as a one-dimensional problem in R space, oh well, it could come. So there you would do this. Suppose you have, say, some potential like this V effective of R versus R, and it goes to infinity, and let's say it's something like this, and let's say it goes. Let's choose something like this, or it could go above. It doesn't matter. Okay, so if you choose some energy, we'll have some turning points, right? So if you think of it as in a 1D problem, it can go to this R, so there'll be an R min and an R max. It will come back to R min. Okay, but so if R is R min, It can come back to r min, but we don't know what will happen to theta prime and phi. Okay, and let's say, I mean, we can ignore actually theta because it's central force motion, but it's more about, so theta is, actually theta is meaningless, so theta is pi by 2, we can choose that. So it will always remain at pi by 2, no problem. But phi may not come back to itself, so it may not close, okay? So you need it to close in the phi space as well at the same time. It could come back to the same value of phi, but at some other r. So then again, it doesn't work. So generically, okay, closed orbits don't happen. Okay, but of course you could always create a circular orbit where everything is kind of fine-tuned, but that's a very, very special, you see. Okay, but there are two special potentials. Okay, the first one is V of r, which is an attractive k, some positive constant. The second one okay, so here in these two cases, closed orbits occur. Okay. Of course, in the 1 by r potential, there are also open orbits. So this is an isotropic oscillator. Okay. So here, I mean, there's no issue. Time period will be just determined by omega. All of them are the same time period. So omega is just 2 pi upon t. But out here, we will solve this problem. So these two are very, very special. Okay. And also, we can, this is one of properties. Second property is we can actually write, we can actually carry out the formal integrals at least. Okay, so I think I'm done for today, and we will. So this is isotropic output. This thing, and this is, for instance, it could be the Kepler problem. It could be hydrogen atom. These are two examples where this potential of this kind comes. Okay, so I'll pause here, and you can ask questions. Okay, I guess everything is, yeah. Go ahead.
When we say angular momentum is constant,